Let's say you're parked on the side of the road. A driver of another vehicle is traveling while holding their horn down. The horn normally produces a sound with a frequency of 440 hertz when that vehicle is stationary. But since it's moving toward you at 15 meters per second, what frequency would you perceive the horn to be? So we can use the Doppler effect formula for this. What's going to happen is when you're observing the sound of the moving vehicle, waves will get compressed as they head toward you, and waves that are headed the opposite direction would be stretched. Sound is still going to travel at the speed of sound, which is 343 meters per second, but the fact that the driver is moving is what creates the compression of the sound waves. So we're going to call V the speed of the waves. So that needs to go both here, above, and below in the formula. Now we need VO, which is the velocity of the observer relative to the source. In this particular problem, they said that we were just sitting in our own vehicle parked. And so I'm going to consider the person to be stationary, having a velocity of 0 meters per second. So let's put just a 0 in for VO. When it comes to the velocity of the source, that's actually going to be the velocity of the moving horn. So it says here that the horn's moving toward you at 15 meters per second. We'll call that VS. So put that down here. When the source is moving away from you, that would be an addition. So you'd want to use positive for moving away, and let the VS be negative when the source is moving toward you. So in this case, since the horn is heading toward me, I'm going to make this a negative 15. Then we have to multiply by the frequency of the source, which is called Fs in this version of the formula. That's the frequency of the source emission when it's at rest. And so it says here in the problem that normally this car's horn would be having a frequency of 440 hertz. With this formula, we should be able to calculate the perceived frequency of the sound when the horn is moving relative to you. This will result in a fraction where we have a bigger number over a smaller number, and therefore that would increase the frequency. That's what we need in this case. We need for the person to perceive a higher frequency because we can see a shorter wavelength between waves. And so when the lambda goes down, that means that the frequency is going to go up. I get 460 hertz. Now, if we change the problem around to where you're observing the car moving away from you at 15 meters per second, now you're going to have a larger wavelength, and therefore we need a smaller frequency. For that calculation, we'll now make the 15 positive. And now we'll have 343 over 358. And I get 422 hertz. So we perceive 460 hertz when the horn is heading toward us, and we perceive 422 hertz when the horn is moving away from us. Even though the vehicle is moving away from us, sound will still travel in air at the same speed of 343 meters per second.